In addition to a measure of central tendency, it is generally desirable to have a measure of dispersion. A measure of dispersion, or measure of variability as it is sometimes called, is an indication of the clustering of measurements around the center of the distribution, or conversely, an indication of how variable the measurements are. Measures of dispersion of populations are parameters of the population, and the sample measures of dispersion that estimates them are statistics. The difference between the highest and lowest measurement in a group of data is termed the range. If simple measurements are arranged in increasing order of magnitude, as if the median were about to be determined, then sample range is as xn divided by x1. This data is a hypothetical set of data in which x1 is x1 is 1.2 gram and xn is 2.4 gram. Thus, the range may be expressed as 1.2 to 2.4, can be expressed as 1.2 to 2.4, or as 2.4 grams divided by subtract of 1.2 grams equals to 1.2 grams. We might bear in mind that x1 is really within the limits of, this is within the limit is 1.15 to 1.25, and xn is really 2.35 to 2.45. So this at 1.2 is a midpoint of 1.15, and 2.4 is midpoint for 2.35 to 2.45. So the range here of the sample would be expressed by a few authors as 2.45 divided by 1.15 equals to 1.3 grams. So quite not similar from the one that we measured before. Note that the range has the same units as the individual measurements. The range is a relatively crude measure of dispersion, as it does not take into account any measurements except the highest and the lowest. Furthermore, since it is unlikely that a sample will contain both the highest and lowest values in the population, the sample range usually underestimates the population range. Therefore, it is a biased and inefficient estimator. Nonetheless, it is useful in some circumstances to present the sample range as an estimate of the population range. Taxonomists are frequently concerned, for example, with having an estimate of what the highest and lowest values in a population are expected to be. Whenever the range is specified in reporting data, however, it's usually a good practice to report another measure of dispersion as well. The range is applicable to ordinal, interval, and ratio scale data. As is evident from this data, the range conveys no information about how clustered about the middle of the distribution the measurements are. Since the mean is so useful a measure of central tendency, one might express dispersion in terms of deviations from the mean. So these are the means of the sample 1.8. So there is also thinking of how much each data point has deviated from the sample mean. So the deviation will be xi minus x bar. So 1.2 minus 1.8 is equals to negative 0.6, and followed by negative 0.4, negative 0.2, 0, 0.2, 0.4, and 0.6. The sum of all variation will always be 0. However, such a summation will be useless as a measure of dispersion. To sum the absolute values of the deviations from the mean results in a quantity that is an expression of dispersion about the mean. Dividing this quantity by n yields a measure known as the mean deviation or mean absolute deviation of the sample. So the mean deviation, sample mean deviation is calculated by the summation of absolute xi minus x bar divided by the total number of the sample. This sample mean deviation expresses the differences in the dispersion. Mean deviation can also be defined by using the sum of the absolute deviations from the median rather than from the mean. So this all is a deviation. When you have the absolute one, this will become 0.6, 0.4, 0.2, 0, 0.2, 0.4, 0.6. This will be equals to, so this will be 2.4. So the mean difference will be 2.4 divided by 7 is equals to 0.34 grams. Another method of eliminating the signs of the deviations from the mean is to square the deviations. The sum of the squares of the deviations from the mean is called the sum of squares, abbreviated as SS, not short SNI, yeah? And is defined as follows. So sample sum of squares is equals to xi minus x bar squared. So this is for sample. And for the population sum of square is by mu. So this is the population. This is for population. So the mean sum of squares is called the variance, okay, or mean square, the letter being short for mean squared deviation, and for a population is denoted by sigma squared using the lowercase Greek letter. So the sigma squared is equal to summation of xi divided by mu, or the mean of a population, divided by capital N. So the best estimate of the population variance is the sample variance, called S2, which is this is equals to xi divided by x bar. X, wait, where's the color? Oh, sorry. So I will try to erase this one. Okay. So S sample square is equals to x bar xi minus the x bar squared, and then divided by n minus 1. The replacement of mu and with x bar and also capital N and smaller n in this equation results in a quantity which is a biased estimate of population variance. The dividing of the sample sum of squares by n plus 1 n minus 1, sorry, which is called the degrees of freedom. Sometimes they call it a degrees of freedom, df, or sometimes they call it degrees of freedom. Okay, rather than by n yields. Okay, why we need to have minus 1 here is to make sure that it can be an unbiased estimate. And it is equation which should be used to calculate the sample variance. If all observations are equal, then there is no variability and the sample variation will be equals to 0. And sample variation becomes increasingly large as the amount of variability or dispersion increase. Remember that if the value of sample variation is increased or higher, okay, or higher, it means that the large amount of variability and dispersion. Since sample mean is a mean sum of squares, it can never be a negative quantity. So there's another note also, this I want to put red here. So sum of square or a sample variance, because of the square here, there is no negative value. So if you get a negative value, means you have something wrong on your calculation. So remember that the sample here, the sample sum of squares, this is the equation for sample sum of squares, is the summation of xi minus x bar square. Since the calculation of sample variance can be tedious for large samples, but it can be facilitated by the use of the equality. So this, this equation can also be denoted as, so sum of squares here can be denoted by the summation of xi square, okay, minus the summation of xi square divided by n, which means that if you do this x1 minus x bar, you need to calculate the mean here first. So then you go up here and then you do all the calculation again. But with this information, you don't need to calculate the mean first. You don't need to calculate the mean. Instead, you just use the x1 and then straight away square it, and then you get the data. So this is x1. So you get x1 square, and then you get the formulation, the summation here. And then the next one, you just calculated this and then divide it by n, right? Then you get you get this, and then the next information is you just use this information and divide it by n. Although, yeah, you look at, I just explained just now, although this formula looks complicated, okay, then this formula, okay, just the way I showed you just now, it is more simpler to operate in this kind of data rather than this one. Therefore, since simple variance equals to sum of square divided by s, so sample variance equals to sum of square divided by degrees of freedom. So this is sum of square. So you get it like this formula. Okay, and then divided by the degrees of freedom. So you get this information easily, then you get this information ready, just based on one table. This last formula, okay, is always referred to as a working formula or machine formula. because of its computational advantages. There are in fact two major advantages in calculating a sum of square by this equation rather than this equation. First, fewer computational steps, just told you before, are involved. A fact that this can decrease the chances of error. Okay, on a good desk calculator, the sum quantities, the sum quantities for this one and the sum quantities for this one, okay, can both be obtained with only one pass-through data, whereas this equation, okay, requires one pass-through data to calculate x bar. So you need to calculate the x bar first here. So you need another step, and at least one more pass to calculate and sum the squares of the deviations. So x minus x bar. So there is another step we need to do. Secondly, the second advantage is there may be a good deal of rounding error in calculating, okay, this xi minus x bar. Okay, let me pause a little bit and then let me clear the screen here. Okay, again, the second advantage is there may be a good deal of rounding error in calculating each xi minus x bar here. So probably people will tend to round up this data, and then the error will increase, a situation which leads to decreased accuracy, okay, in computation, but which is can be avoided by this equation. Okay, let's do some calculation or try to test this formula. Let's say you want to use this simpler formula. Simpler means simpler in terms of the equation. Okay, so you need to find the mean, the x bar here. So the x bar here is the total, and then you can get here is 1.8 grams. Okay, so this is what the first step you need to do. Later on, you need to find the sum of square here first. So the sum of squares here, see, you can well 1.2 minus 1.8, and then you square it. So you get this information, and then you do all the way down, and then you get the sum of squares for this sample. So this is the two steps increase for this one. However, if you use the second formula, you can skip all these two other steps here. You just directly square the all values on data points, and then you get the first one. So you get this first summation of xi square. So this will be the summation of xi square. So, and then for that reason, for this one, you only have this one data, and then later on you just did put the data here. So this will be the summation for x1 square will be 23.8 grams. So this is summation of x1. So only for using this data, you can straight away put into the formula. So 23.8 grams divided by 23.8 divided by n. N is 7 here, and straight away 7 minus 1. So you get s square, or sample variance, equals to 0.1867. So this is why this formula is called as working formula or machine formula. Okay, just now we just make the variance for the non-group or non-group data. So how about the data for frequency data? Like let's say frequency table, how to calculate the variance. So remember that this is for the formula for non-group or non-frequency data. This is a sum of square for the sample. So for sample sum of square for frequency data will be, okay, almost similar to the non-frequency data. The only difference is we put the frequency over there. So Fixi square minus the summation of Fixi square divided by n. So these are the sum of square for frequency data. So the first thing first you need to do when you have the frequency data and you want to find the sum of square, you need to look at the class here. So this is usually we need to find the midpoint. So sometimes they call it as X and P. Okay, so the midpoint, so this is the range, so you need to find the midpoint. So how to find the midpoints? Lower plus higher boundaries divided by 2. So this is 0.3, this is 1.5, this will be 11, 5.5, this is 19, so 9.5, so 13.5, so this will be 17.5, and then you can calculate so on and so forth. You can try to pause this video and then try to complete the midpoint value. So next, what we need to do is we add another 2 columns here. So the first one will be the Fixi squared, and another one is F1xi. So we need to find these two values first. So what we are going to do is, for this one, this will be complementary for this one, right? So F1xi, so you have 6 over here, and then you times 1.5 square, and this will become 13.5. And then try to do the rest. This is 17, so 5.5 square, so 49.5 square, and so on and so forth. Try to continue down here. So this will get the Fixi square, and then this will get the summation of this. Then you get all this down here, so that you can get this Fixi square first. And then for this one, for F1x1, you just directly put 1.5. Sorry, so Fi 6. Sorry, 6 times 1.5. So this will become 39. Okay, so then do the rest. So 17 times 5.5, 40 times 9.5, and you do the rest. So the summation of Fixi here, then you can put the value here, and then you can also put the value here. So this will be, then you will get the sum of square of this frequency distribution table. So now I've already completed the table here. So next what we need to do is just to put in all the data to the formula. So first thing first, that you need to know that there is the first one is to get the sum of square here. So first you need to know the summation of F1x1. So this is F1x1 square, so which means that the total will be 213534. So this one we get straight away 213534, and then minus 2 Fixi. So Fixi has the total of summation of Fixi here 6605 0.5, and it must be square here and divided by n. N is 424, the total numbers of samples, so 424. So remember, this is a sum of square, right? So then you get it 213534 divided by, so this I already counted the square for the Fixi. You get the 4362 SIX1003 divided by 424, and then you get all this. You get this is the sum of square, 21250.1. So this is the sum of square for this sample. So later on, what you need to do is to find the variance. The variance is just simple, so means that the variance is the sum of square divided by degrees of freedom. So which means that 212505.1, which is this is a sample, means the degrees of freedom is 424 minus 1. So this is 0.1. So the total will be this one. This will be the variance. So this will be the sum of square for the sample, and then this is really the variance for the sample. Okay, I hope by now you already understand about how to calculate the variance based on the data, either is the group or ungrouped. The later on is on the next one. What you need to do is to find the standard deviation. So the standard deviation is the positive square root of the variance. Okay, so it's just simply as so. This is the square root of the variance. So this, or let's say this is a population mean. So this is a population variance and this is sample variance. What you need to do is just square root the variance. So then you get the standard deviation. So this is for the population. So this is the standard deviation for the sample. So no need to be complicated. If you want to get the standard deviation, first get the variance first, and then just square the variance. Then you can get the population standard deviation and also sample standard deviation. So remember, with the square root, with the square is the variance. So this is the variance. So without the square, this is the standard deviation. So once we have the standard deviation, excuse me here, once we get the standard deviation, so once we get this information, the next thing that we can calculate is the coefficient of variation. The coefficient of variation or coefficient of variability always defined or always expressed by denoted by CV or sometimes capital V. Okay, so this is equals to standard deviation divided by mean. Okay, or you can do the standard deviation for the population divided by mean. So this is a coefficient variation. So generally this also expressed as percentage. So this also can be standard deviation. So let's say the standard deviation by times by 100. So this can become this coefficient variation will be expressed as percentage. As a measure of variability, the variance and standard deviation have magnitudes which are dependent on the magnitude of the data. For example, elephants, they have ears that are perhaps 100 times larger than those of mice. If elephant ears were no more variable relative to their size than mouse ears relative to their size, the standard deviation of elephant ear would be 100 times as great as the standard deviation of mouse ear length. So the coefficient of variation expresses sample variability relative to the mean of the sample and is on rare occasion referred to as the relative standard deviation. So it is called a measure of relative variability or relative dispersion. Since standard deviation and also mean have identical units, coefficient variation has no units at all, a fact which emphasizes that it is a relative measure. divorced from the actual magnitude or units of measurement of the data. Thus, therefore, coefficient variation give us some interpretation of relative deviation of the population or the samples or the data from the sample or population mean.